dear students. Today, we are going to do more questions, PYQs from haloalkanes and haloarenes. We are almost winding up with haloalkanes and haloarenes chapter. Let's see what are the questions which I brought for you today. Hi, I'm Prasanna and welcome to my platform, Chemsmart. Question number 1 is consider the following compounds. First one, you can see it is cyclohexyl chloride. Second one is chloromethyl cyclohexane. And the next one is chlorobenzene. And question is about correct order of reactivity towards SN2 reaction. You know, SN2 reaction depends on what? It depends on the steric hindrance surrounding the electrophilic carbon, the positive carbon, means to which the halogen is connected. Clear? And you know what is the order of reactivity in SN2 mechanism. What is the order of reactivity in SN2 mechanism? In SN2 mechanism, the order of reactivity is methyl halide greater than primary alkyl halide, greater than secondary, greater than tertiary. Because this is the order in which the steric hindrance increases. When steric hindrance increases, reactivity will decrease. Steric hindrance around the electrophilic carbon. Now, let's see what is the nature of these alkyl halides, these halides given. Here you can see in the first case, it is chlorine connected to this carbon. So this carbon is connected to two other carbons. So it is a secondary alkyl halide, equivalent to secondary alkyl halide. It is cycloalkyl, secondary halide. Here this chlorine is connected to this carbon, which is connected only to one other carbon. So it is a primary alkyl halide. This is not an alkyl halide, it is haloarene, where there is partial double bond character between the carbon of the benzene ring and the halogen. So, no way that it is easily cleaved in SN1 or SN2. Understand? So, forget about this. That is haloarene. That will be the least reactive, whether it is SN1 or SN2. Now, what will be the order here? Primary more than secondary, more than, here it is haloarene. Okay, among the compounds given to us in the question. So primary is what? Second one. Secondary is the first one. And the least reactive will be the third one. So what is the order? 2 more reactive than 1. That is primary more than secondary, more than the haloarene. Therefore, what is the correct answer for this question? It is 2, 1, 3. Clear? So, practice such questions well. Let's see what are the options given here. The options given are A, B, C, D. These 1, 2, 1, 3, 2, 2, 3, 1, 2, 1, 3, and 3, 1, 2. So, our correct answer based on our findings is 2, 1, 3. Clear? Now, the next question. Out of CS3 tri-CBr and CS3 tri-Ci, which one is more reactive towards SN1 reaction and why? You know, SN1 reaction is based on the stability of the carbocation. But these two compounds given to you, you can see that the alkyl group is same in both of them, isn't it? The alkyl group is tertiary butyl group here. Here also it is tertiary butyl group. That means the R group is same. And you have studied when the R group is same, the order of reactivity depends on the strength of the CX bond. Means here it is CBr bond, here it is CI bond. Understand? We are comparing the CX bond because the alkyl group is same. Now, if you compare the CBr bond and the Ci bond, which one will be weaker and easily cleaved? You know, iodine is bigger in size. We have discussed in one of the previous sessions. When we go down the halogen family, the atomic size increases and the bond length increases. That is, the CX bond length increases. When bond length increases, bond strength will decrease and it will be easy to break that bond, right? So Ci bond will be weaker because it is longer. Its bond dissociation enthalpy will be lesser compared to the CBr bond, which is shorter. That means I minus will be a better leaving nucleophile than the smaller Br minus. So which one will be more reactive towards SN1 reaction as per the question? It is CS3 tri-Ci. Hope that's also clear. Okay. Now let's go to the next question. Why dextro and levorotatory isomers of butan 2-ol are difficult to separate by fractional distillation? Again, we have studied we have discussed in one of the previous PYQ sessions that the dextro and levo isomers, they are enantiomers, which differ only in optical rotation. One is dextro, the other one is levo. All other properties are identical, including the boiling point. You know, fractional distillation depends on the difference in boiling point. But if the boiling points are same for the components to be separated, do you think it is easy? No. So, dextro and levorotatory isomers means enantiomers, they cannot be separated by fractional distillation because they have the same boiling point, identical boiling point. And this fractional distillation depends on the difference in boiling point. Clear? Great. Now, next question. Write the product formed when para-nitrochlorobenzene is heated with aqueous NaOH at 443 Kelvin, followed by acidification. Let's see what the reaction is. It is para-nitrochlorobenzene. Chlorobenzene, para-nitrochlorobenzene. It is heated with aqueous NaOH. So we are heating it with aqueous NaOH, followed by acidification. You have the same equation in your textbook in the reactions of haloarenes, that is chlorobenzene. You know, nitro group is a withdrawing group, electron withdrawing group. So it can weaken the CCl bond. In the presence of alkali, nucleophilic substitution can happen. Cl can be replaced, Cl minus can be replaced by OH minus, nucleophilic substitution. But of course, it is not easy as it is in the case of alkyl halides. So the answer here will be the Cl minus is replaced by OH minus, and here it will be NO2 group. So we'll be getting para-nitrophenol or 4-nitrophenol. And practice the other two equations also in your textbook. That is, the more the number of electron withdrawing groups, easier will be the substitution of Cl minus by OH minus. They are also previous board questions. Make sure to practice them. Only thing, this one is asked in this paper, that's all. But the other two are also board questions. Make sure to practice. Okay? Now, next question. Write one stereochemical difference between SN1 and SN2 reactions. SN1 reaction we have discussed. It is followed by racemization. Because in SN1 reaction, step 1, we are getting a carbocation. Carbocation, it is trigonal planar. We have discussed it before. So it can be attacked from either side. That means there will be equal proportions of dextro and levo isomers. The two enantiomers will be produced in equal amounts, probability, and therefore it will lead to racemization. So SN1 is followed by racemization, whereas SN2 is followed by complete stereochemical inversion. Do you remember? Just like inverted umbrella in the mechanism you have studied. So SN2 mechanism is followed by complete stereochemical inversion, whereas SN1 is followed by racemization. That is the major difference in between SN1 and SN2 in stereochemical aspect. Clear? Now, the next question. Out of chlorobenzene and benzyl chloride, which one gets easily hydrolyzed and why? Let's see what is chlorobenzene. We have discussed already in the same session here. Chlorobenzene is this. You know there is a partial double bond character between C and Cl due to resonance. Whereas in benzyl chloride, it is like this. It is benzene with CS2Cl. You know this is a haloarene because halogen is directly connected to benzene ring. Whereas this is not a haloarene because halogen is not connected directly to benzene ring. So it is not aryl halide, it is aralkyl halide actually. So what happens here is when the Cl minus is lost, it can be lost easily because it is not on the benzene ring. So it is equivalent to alkyl halide in behavior. So you'll be getting the benzylic carbocation. And you have studied benzylic carbocation is stabilized by resonance. That means this can undergo the nucleophilic substitution more easily compared to the chlorobenzene where there is a partial double bond character. So this one will react faster. Okay. And in another year, the same chlorobenzene was clubbed with cyclohexyl chloride. Means instead of this, they have given cyclohexyl chloride in the paper. But the other party in the comparison was same chlorobenzene. So if you compare these two, again the same thing. Always remember and register. Whenever chlorobenzene is there in the pair, it is not easy for chlorobenzene to undergo nucleophilic substitution. Reason, partial double bond character of the CCl bond. So don't select that. It is difficult for haloarene to undergo nucleophilic substitution. Here, it is a true single bond between halogen and carbon of the ring. So it can be cleaved easily compared to haloarene, and that will undergo nucleophilic substitution more easily. Clear? Okay. Now, the next question. Identify the chiral molecule in the following pair. You know what is meant by chirality? Non-superimposability, right? So, for chirality to occur, there should be asymmetric carbon present or a stereo center present in the molecule. At least one stereo center should be there. Stereo center means, stereo carbon means asymmetric carbon where the carbon is connected to 4 different atoms or groups. That is called an asymmetric carbon. So let us find out which one is having asymmetric carbon in the structure. Look here. Let us take this carbon. You know here, this is CS3. It cannot be asymmetric because 3 hydrogens are repeated on that carbon. So no chance that it is asymmetric. This can also be not asymmetric because it is again CS3. You know the bond line formula, right? Then this is also CS3. Now on this carbon, 1, 2, 3. The 4th valency will be hydrogen, but we don't show it in the bond line formula. That's all. So if you look at this, on this carbon, one group is OH, one group is methyl, one group is hydrogen, and the other group is isopropyl. Okay, it is isopropyl group. So 4 different groups are connected to this carbon. That means this carbon is a stereo center. It is asymmetric carbon. It will be optically active. It is chiral. What about this one? Let's check. No chance here because it is CS3. CS3 hydrogens are repeated. This is CH. Here it is CS3. No chance of being asymmetric. This is also CS3. This is CH. Now look at this carbon. Here, fourth valency will be hydrogen like in the other case, right? So if you look at this carbon, one is isopropyl group. This is again isopropyl group. This is OH and this is H. You can see two identical groups are repeated on that carbon. So no chirality for any carbon present in this molecule. So this is not optically active. It is not chiral, whereas this molecule is chiral, and it is always better. Even though you identify the chiral molecule, better to present that chiral center by putting a star or asterisk. Better presentation if you aim perfection. Clear? Even though they haven't asked, they have asked you which is the chiral molecule. We identify the chiral molecule, but one step ahead, mark the chiral center. Understand? Great. So I hope all these questions are clear to you, how to deal with these questions if they appear in your paper. Okay? So practice these questions well and try to reach your target score in organic chemistry, as well as the entire class 12 chemistry in board exam 2024. So make sure to like, share, and subscribe to my channel. Definitely you will be rewarded for being in my channel, attending these sessions. 100% sure you will be rewarded. Okay? You can see once the board examination is over. So see you inside for the next session. Till then, bye.